Thank you for the opportunity to present our work today. My name is Mi Liu from Hunan University, and I'm present to share our recent research on advanced robotic rebatining with 6 degrees of freedom pose estimation. My presentation is structured into 4 main sections. First, I will introduce the problem of rebatining and the current limitations. Then I will explain our proposed method. Next, I will present our experimental results and finally conclude with key contributions. Let me start with the fundamental of rebatining. Rebatining is a critical procedure in concrete construction, commonly applied in bridges, tunnels, and buildings. Is executed prior to concrete pouring to ensure structural stability by preventing rebar displacement. Currently, rebatining is a predominantly manual work. The process involves 2 main steps. First, looping the tie wheel around the rebar intersection. Then, testing the wheel tightening use tools. However, this manual approach is facing significant challenge. It is extremely labor-intensive, time-consuming, and poses injury risk to workers. Those limitations have driven the need for automatic solutions. Several robotic solutions have emerged to address those challenges. However, there is a critical limitation. Most of those systems are designed for tiny flat plate bars only. There is still a significant gap in robots capable of handling 3D reinforcement skeletons with rebar plane oriented in various directions. To understand this limitation, let's examine the degrees of freedom requirement. Current horizontal rebatining use 3 to 5 degrees of freedom systems. However, for complex 3D reinforcement structures which require tight operation on vertical or inclined surface, we need 6 degrees of freedom systems that provide for translational and rotational capabilities. Pulse information is very important for 6 degrees of freedom robotic arm operation, and it consists of both positional and orientational components. This brings us to the core research problem. Current state-of-art vision perception for rebar tining use deep learning-based keypoint detection, which successfully predict positional information but completely neglect the orientational information. This creates a critical gap between current capability and the requirements for 6 degrees of freedom robotic rebatining. Our research objective is to develop a 6 degrees of freedom tining pose estimation method that enhances robotic capability for handling reinforced skeletons with rebar plane in various directions. Now, let me explain our proposed method. Our method consists of 3 models. Model 1 acts as a processing model to generate input data and prior displacement information for rebar pose estimation. In Model 2, a coarse-to-fine point cloud registration method is proposed to estimate the pose of rebar in intersection areas by computing the transformation needed needed to align the node template with observed date. In Model 3, a symmetry-aware tiling strategy is employed to optimize the conversion from Rebar poles to tiny poles by determining the optimal roll angle. Here is the detailed workflow of our coarse-to-fine registration method. This method consists of two steps as follows. In step 1 of coarse registration, the goal is to achieve a row alignment of template point cloud with Rebar point cloud. This is accomplished by finding the appropriate rotation matrix and the translation vector based on the geometric feature of the template point cloud. In step 2 of fan registration, the ICP algorithm is used to iteratively minimize the alignment error with the template point cloud and the Rebar point cloud. Our symmetry-aware tiling strategy consists of three key steps. First, we predefine multiple tiny poles in the template coordinate frame. Second, we determine candidate tiny poles in base coordinate frame using forward kinematic. Finally, we select the optimal tiny poles based on the minimal rotation angle requirement, which significantly reduce motion time and improve efficiency. Move to our experimental results. Two experiments will conduct to validate the proposed method. Experimental 1 aims to test the effectiveness of the proposed coarse-to-fine point cloud registration method. Furthermore, experiment 2 explored the effectiveness of the proposed symmetry-aware tiling strategy for 6 degrees of freedom tiny post estimation in Model 3. The result of experimental 1 demonstrates superior performance of our method. In registration accuracy and computational efficiency, our method significantly outperform competitors, outperform other methods like ICP, RANSAC, and CPD. In experimental 2, we selected 4 different poses across various scenes. The results demonstrate that the proposed strategies consistently outperform fixed template method, achieving substantial time saving in practical application. In conclusion, this research makes several key contributions. First, we have developed 6 degrees of freedom tiny post estimation that enable Rebar tiny robots to perform operation on reinforcement skeletons with Rebar planes orientation in any direction. Second, our coarse-to-fine point cloud registration method significantly address textureless surface and self-occlusion challenge. Third, the symmetry-aware process optimization minimize motion trajectories through optimal roll angle determination. In summary, our research successfully advanced robotic rebar tiling from 2D to 3D reinforcement structures through 6 degrees of freedom post estimation. Thank you to my co-authors and the ISARC 2025 organizer. Thank you.